Thank you, and good morning, and thank you for the invitation to talk to Pendleside Probus Club. So this is going to be a talk, as you can see, on the A, B, and C of galaxy evolution.
Can everybody please go to the board, right? It's not mine. Sorry, Steve.
Okay, so originally this was going to be perhaps close to an hour. I've taken a couple of slides out, and I'll see if I can get it down to about 45 minutes or so. So this is a talk about how galaxies come to be. When we look out into the universe, we find the universe is full of galaxies. We live inside one, and there are trillions of others. The question is, how did these galaxies come to be the way they are? So in many cases, when we look at galaxies, we find beautiful spiral structures. In some cases, we find galaxies interacting with each other, producing weird and wonderful shapes. Sort of classic spiral structure, sort of a Catherine wheel sort of shape, for instance. And in some cases, a rather more dramatic, in this case, two spiral-armed galaxy with a very large bar in the middle. But the question is, how did all this come to be? And what are the key factors that determine that's the way the universe works? That's what I call the ABC. And the ABC are as follows. A is for accretion. That's how galaxies form, by the accretion or the accumulation of matter that was made in the Big Bang and has been accumulating and accreting ever since, over the last 13.8 billion years or so. What's going on at the center of most galaxies? We think there are black holes, supermassive black holes far more massive, for instance, than the mass of our sun. And it looks like there are supermassive black holes at the center of every galaxy that we look at, including our own. Some of these black holes are feeding, in the sense that matter is falling into the black hole, generating lots of energy. Other black holes are more quiescent. And finally, the C of the ABC is collisions. Because one galaxy colliding with another, it sounds like a very dramatic event, the fact that you can get a galaxy with many billions of stars in it colliding with another galaxy. But this is how galaxies evolve. This is how they have evolved over the billions of years since they were originally created. So I'll say a little bit about how these three influence the structure of galaxies. So where does the story start? Well, I haven't got time to recap everything, but in a different talk, I talk about the beginning of everything. In other words, how the universe came to exist. The beginning of everything, 13.8 billion years ago. It took about 3 minutes to make all of the hydrogen and helium, all of the gas in the universe, which ultimately will be used to make the stars which form the galaxies that we're talking about. When we look into the universe, we realize the universe is expanding, and so if the universe is expanding and everything is getting further apart on the largest of scales, we can deduce that in the past, everything used to be a lot smaller, everything used to be a lot closer together. And although it sounds fairly ludicrous, we can now work out that if the galaxies are this far apart at the moment and the observable universe is some 100 billion light years in diameter, if we go back far enough, we go to a time when the universe, the observable universe, which is currently 100 billion light years in diameter, was approximately the size of a golf ball. Now that takes a little bit of imagination. Yes, I agree with that. It's difficult to actually sort of comprehend what we must be talking about, but the logic is, if everything is moving further apart, then in the past everything used to be a lot closer together. So it is thought, it is hypothesized, that the universe used to be about this size or so. And just like a golf ball, it had dimples in it. In other words, it had variations in density, variations in temperature. And we know that because when we look into the sky now, if we look in the radio part of the spectrum, we see the so-called microwave background. There are microwaves coming from all directions in space, and we interpret that as being effectively the afterglow, if you like, of the Big Bang that occurred 13.8 billion years ago. So we have reasons to believe the universe used to be a lot smaller, and we have reasons to believe it was dimpled in the sense that there were variations in density. And the question is, how did we go from something the size of a golf ball with a few variations in it to something that we now see when we look at, for instance, the Hubble Space Telescope, we look in the deep field, we take a long exposure of quite a few days, we see many thousands of galaxies, implying that there must be many trillions of galaxies out there. How do we actually understand that process of going from the creation of the universe to where we are now? Well, we can just sit and think and scratch our chin and say, well, I think I understand the physics, so I figure out what's going on. But our real advance in understanding how the universe works is based on simulations. In the last few decades, it's been possible to run simulations on supercomputers that allow us to test some of the ideas we have. In other words, if we start with a lot of mass and then let gravity do its stuff, do we end up with a universe which looks like the one in which we live? If it is, if we can get that to work, then maybe the simulations are telling us something about the real universe rather than just a hypothetical one that lives in a computer. So there are lots of different simulations. I'm not going to talk about the details, but lots of people have written computer simulations to try and answer the question, if we start with a whole load of matter made in the Big Bang and let gravity work, do we end up with the sort of galaxies that we see today? And I'm just going to take a small number of those simulations and I'm going to borrow some videos and images from those simulations to illustrate what I'm talking about. And I'll give you the link, which is also available in a handout of the slides. There's also a web link if you want to go and look at these simulations for yourself. So if we start with a golf ball and allow it to expand and let gravity do its stuff, what do we actually see? Well, here's the first of the simulations. We're starting with effectively a cube. It just, of course, looks like a square because I can't show a full three-dimensional structure. But we're starting with a cube of space in which we've got some variation in the density of matter, and over billions of years, we're just going to let gravity do its stuff and see what happens. Gravity is going to take hold of some of the slightly denser regions and condense them and concentrate them, and others will look a little more rarefied. So this is what the simulation looks like if we allow it to run. The brighter areas are the denser areas. So gravity is slowly collapsing this structure, and you're seeing some bright areas, some knots, if you like, are starting to form in this web-like structure, which is comprising filaments and voids, and it's often called the cosmic web because on the largest of scales it does look rather web-like. You see these little strands of matter, and where these strands or so-called filaments intersect with each other, we get these white blobs. These are where matter is flowing down the filaments and condensing or concentrating into areas which ultimately will become the galaxies that form the stars that form stars like our sun and eventually planets. So we'll have a look at a little more detail at what's going on in one of these white blobs in just a moment. But it's worth pointing out that it's not just a question of throwing this into a computer saying, let's start with some mass. We know how gravity works. Newton figured that out hundreds of years ago. Okay, Einstein had a little bit to say about that, but for most of what we need, Newton is good enough. It's not just a question of gravity and matter. We have to take into account the fact that as things collapse, stars are born. And when stars are born, stars live and stars die, and we can get supernova explosions. So these red bubbles here forming in this three-dimensional structure, which we're now sort of spinning around, because stars can be born during the process of gravitational collapse, and because of the way supernova can blast material out, and indeed black holes can blast material out as well, that can impede matter falling in. So gravity is trying to pull everything together, but as stars are born and as they live and as they die, there can be an outflow of gas as well. And if we want to simulate all of this, if we want to predict how the universe ends up looking like it does now, we have to build in not only gravity, we have to build in these effects, these astrophysical effects, to make sure that we model everything realistically. And the question is, can any of the simulations that we've been running for the last few decades, can they actually explain the diversity of galaxies that we see? We know that there are trillions of galaxies out there. Hubble Space Telescope has mapped some of them, perhaps thousands, perhaps tens of thousands, only a tiny fraction of the total number. But we already realize that we can sort of put them on this sort of chessboard, if you like. Some galaxies appear to be disk-like, spiral galaxies. They tend to be a bit bluer in color and rather flat, whereas other galaxies on the right-hand side of this diagram tend to be a bit redder, and they tend to be more elliptical, more rugby ball shaped rather than flat disk galaxies. So can our simulations account for this diversity of different galaxies in the universe? So let's have a look at the process of accretion. Before we get stuck in and look at the first simulation of how accretion produces a galaxy, let me just say something about the simulations themselves. So this particular suite of simulations, called Illustris, they're basically running over a period of time from the Big Bang itself all the way up to the present day. And as I've mentioned, it has to take into account not only the effects of gravity, but the effects of everything else that we can think of that could possibly affect the way that stars and galaxies come into being. As well as black holes and supernova being generated when we're thinking about matter accretion, we also have to worry about this first panel, the fact that the universe is not full of what we think it is. Relatively recently, like a few decades ago, it was realized that the universe, despite the fact that when we look out into the universe, we see trillions of galaxies, each of which has got hundreds of millions, hundreds of billions of stars in it, most of the universe isn't what we can see. In other words, what we can see in terms of stars and dust and gas and everything that's luminous is actually only a tiny fraction of everything that's in the universe. And unfortunately, there is this stuff we don't understand called dark matter, which appears to be out there, but we don't fully understand what it is, in the sense that we don't know, is it a particle we haven't found yet? Is it a type of star that appears not to be shining? We don't understand the origin. All we know is that the matter is there because we see the evidence that the matter is there. In much the same way that you can see trees blowing in the breeze, so you can deduce the existence of the wind, even though you can't see it, simply from the response of the boughs of a tree. And similarly, by looking at the way things behave in terms of stars going around galaxies or galaxies moving, we can infer the existence of a whole load of matter that is not the visible matter that we see in the universe. This has to be taken into account in the simulations. The Illustris simulations ran for about 20 million CPU hours, in other words, 20 million computer hours, if you like, over a period of a few years ago. Having done those simulations, they then realized, the people who wrote the code, the people who ran the simulations, realized that they could do a better job, so they decided to rewrite the code and produced a more sophisticated simulation. So having produced Illustris version 1, did they then name this one Illustris version 2? No, they were Star Trek fans, so they called it Illustris the Next Generation. So hereafter, I'll simply talk about TNG. TNG is the accepted abbreviation for the set of simulations, the second iteration, if you like, of these Illustris simulations. So Illustris TNG ran for 200 million CPU hours over a period of a few years. These simulations ran on supercomputers, in this particular case, a set of Cray supercomputers, just to give you a sort of sense of scale. If you ran this code, this program, to try and simulate the effect of gravity on matter and the astrophysical effects that will then produce galaxies, if you ran it on, for instance, a desktop PC, then it would take something like 20,000 years for the program to run. So you really do need supercomputers to be able to run this in a matter of weeks or months rather than tens of thousands of years. So it takes a lot of expertise to get the simulation right, and it takes a lot of computing power to run the simulation. And then, of course, it takes an army of PhD students to interpret the results and see if it all makes sense, having run the code. The scale on which these calculations were done, rather than try and simulate the entire universe, which is too big a problem to do in one go, what they tend to do with these simulations is to say, right, we're going to look on different scales. So in other words, we're going to think about what's going on a scale of 300 million parsecs. A parsec is about 3 light years. So on a scale of 300 million parsec, that gives us the large scale structure of the universe, and hopefully that will allow us to simulate the cosmic web, these filaments and voids of galaxies that exist, which we do indeed see when we look out into the universe. But that's a rather large scale, and we want to see detail, so we'll also run on a much smaller scale so we can see more detail of what's going on with individual galaxies. And that will be on a scale of 50 million parsecs, or 150 million light years. And just to make sure everything ties together, we'll do an intermediate scale as well, on the 100 scale. So TNG 50, 100, and 300 refer to the different spatial scales that are done for the simulation to try and get the large-scale structure as well as the small-scale structure of the universe. And just a reminder about this business of light years and parsecs. A parsec is used by astrophysicists. It tends to be used by astrophysicists. A parsec is simply 3 and a bit light years. Amateur astronomers tend to prefer light years because it's more intuitive, the distance light travels in a year, but astrophysicists prefer using parsecs for reasons I'm not going to go into. So just as a rough sort of yardstick, as it were, if we think about the size of the Milky Way galaxy, it's about 150,000 light years across, which is about 50 kiloparsecs. And the distance from one galaxy to another, well, that can vary, but if we think about how far it is from our Milky Way galaxy to our neighboring galaxy, the Andromeda galaxy, that distance is about 2.5 million light years, and so that's about a megaparsec. So parsec is actually quite a useful yardstick because, roughly speaking, parsec is typically the distance between stars, and a megaparsec, a million parsecs, is roughly the distance between galaxies. So obviously there's a bit of variation there, but it's a useful reminder. Parsec, distance between stars; megaparsec, distance between galaxies. So let's have a look at this simulation and see if we can see what's going on here. In this particular case, the color coding is supposed to show us where material is ending up. So we're looking at one of these little bright knots that I showed in the earlier simulation. Matter is feeding down these filaments. Remember the cosmic web with filaments and voids. Matter is streaming down these filaments and collecting in this central region. And as the material gets denser and denser, the color coding here gets more and more yellow. So the material is flowing down from the top, and it's flowing in from the bottom left, and it's flowing in from the bottom right. Material is flowing down these filaments as gravity is taking effect, and it's starting to accumulate in this central region. And you can see it's starting to swirl like water trying to go down a plug hole. It's swirling, and we're starting to see the elements of the structure of a galaxy. We can't yet see clear spiral arms, perhaps, but notice that the background is now getting very dark. A lot of the material has now been dragged out of these filaments and is collecting into this central region, and this is starting to form a slowly rotating galaxy. This simulation was carried out over a few billion years. It might take perhaps 100 million years or so for a galaxy to rotate once, typically. So we can get a feel for how material flowing down these filaments starts to collect into these regions which become galaxies. If we look at the large-scale simulation here shown black on white to make it a little easier to see, we see the structure, this web-type structure in the background, and if we zoom into particular knots in these filaments, we start to see individual galaxies in the simulation. And the question is always, do the simulated galaxies look anything like the actual galaxies that we see in the universe? So if we look at these little simulations here, and then we compare them with actual observations, pictures taken by the Hubble Space Telescope, there's a couple of galaxies interacting with each other, looking very similar to this simulation. There's another couple of galaxies looking very similar to this simulation. There's another galaxy which appears to sort of have shells of stars around it, looking very similar to this simulation. So yes, every simulation that's carried out will have a number of different galaxies generated, and on the whole, there are galaxies out there somewhere in the universe which bear a striking resemblance to these simulations. What we don't tend to do is simulate galaxies that look nothing like the galaxies that actually exist, and vice versa. We don't usually fail to be able to predict the existence of galaxies that we do see. If we want to see more detail, rather than just a smudge here and a smudge there, rather than look on the scale of TNG 300, the largest scales of the cosmic web, we need to look on a smaller scale of TNG 50 to look at the detail of individual galaxies. And then we can really start to ask ourselves, well, if these are the sorts of galaxies that are simulated in these sorts of calculations, do they look sensible? And the answer is yes, we do indeed see lots of galaxies that look like this when we look out into the universe. The left-hand side here is showing where the hydrogen is. They're simply color-coded to say that in this galaxy, the red or yellow regions are where the hydrogen gas tends to concentrate, which is where you would expect the stars to be born. And the right-hand side is, given our understanding of how stars are born, where would we expect the stars to be shining in these galaxies that are part of our simulation? And for anybody that's ever looked through a telescope at small galaxies, or even just thumbed through astronomy magazines or looked at pictures from the Hubble Space Telescope, it's fairly clear that these are precisely the sort of galaxies that do actually exist out there. So the simulations do appear to do a good job of simulating galaxies. Not only galaxies in general, but of course the one that is particularly interesting to us is, can these simulations actually generate a galaxy like the one in which we live? In other words, the Milky Way galaxy. And yes, the illustrious simulations do indeed generate lots of galaxies with masses or with numbers of stars which are of order 100 billion stars or so, in other words, about the size of the Milky Way galaxy. And the structures of the galaxies that are generated are very similar to the Milky Way structure. It's difficult to tell what the Milky Way looks like. It's a bit odd to say we know more about other galaxies than we do our own. Because we're on the inside looking out, it's sometimes difficult to work out what the structure of our own galaxy is. But we are fairly sure that we live in a spiral galaxy with 4 spiral arms. As seen face on, it looks a little bit like this. And as seen from the side, it's a bit 2 fried eggs back to back. That's the way to visualize it. So the bulge of the center of the galaxy is that little bright spot in the middle, and the rest of the disk, the rest of the spiral arms, are relatively flat when seen edge on. And yes, these simulations are capable of generating large numbers of galaxies that look very similar to our galaxy. So we believe that means that we've got some confidence that these simulations are telling us something useful. How do we know what's going on in the centers of galaxies? Well, we've known for a while now, or at least we've suspected for a long time, that there are black holes at the centers of galaxies. How do we know? Well, one way we can do that is to look at stars orbiting close to the center of the Milky Way. We've worked out a while ago roughly what the structure of our Milky Way galaxy is. We know where the center is, so we can look towards the center and we see a number of stars moving quite quickly. Stars are orbiting around something we cannot see. There is something large and massive holding those stars in orbit, but there doesn't seem to be anything visible. So if it's large and massive but not visible, then black hole was certainly a candidate very early on. And over the last few years, we've confirmed that by mapping out using telescopes on Earth and watching for months and years at a time, watching individual stars orbiting around something that's out there by tracking lots of stars and using our knowledge of Kepler and Newton telling us how objects move under the influence of gravity. We've managed to determine that something is keeping those stars in orbit, and that something must be very massive. It must be a mass of approximately 4 million solar masses. That symbol there, capital M, circle dot, is just astronomers' shorthand for the mass of our sun. There's nothing particular about the mass of our sun. It's just a better unit than talking about kilograms or tons. So the object holding those stars in orbit has got a mass of some 4 million times the mass of our sun, but it must be quite small, otherwise these stars would go banging into it. So it must be actually quite tiny. It's thought that that object must be considerably smaller than our solar system, for instance. So it's got the mass of more than 1 million times our sun, and yet it's physically quite compact. And so we believe it is a so-called supermassive black hole, SMBH. So you could say that, okay, we are living in a Milky Way, and when we look out, we see the Milky Way as a band of light across the sky, and we deduce that our Milky Way has got a supermassive black hole of 4 million solar masses. But that's by no means a record. We look at other galaxies, such as Centaurus A. We believe that's got a supermassive black hole at the center. You can't actually see it in this picture, but it's somewhere in that red circle. We believe that that has a mass of some 100 million solar masses, and that's by no means a record either. We can see the existence of black holes because if stars get too close to a black hole, they can be disrupted and the matter can end up getting sucked into the black hole. Notice that all the matter just doesn't go down the plug hole in one go, it circulates around. And generally speaking, the circulation of matter waiting its turn to go into the black hole, that matter gets heated and that radiates light. So it's not energy coming from inside the black hole as such, it's energy coming from the region around the black hole because of the very strong gravity that the black hole exerts. Sometimes we also see jets, which we don't fully understand. Not only do we get this so-called accretion disk of matter circling and radiating electromagnetic energy, such as light or radio waves, but sometimes we see energetic jets of particles coming out of these black holes. And we don't fully understand the mechanism that is generating these particular jets. We've seen it before. For instance, this galaxy, rather remote galaxy, appears to have a little spike coming out of it in one sort of quadrant, as it were. With the Hubble Space Telescope, we can see that in a little more detail. We think this particular galaxy is generating jets back to back because that's the sensible way of generating jets. But it just so happens one jet is coming towards us, and that's very bright, and the other jet is going away from us, and that's rather faint, so we only tend to see one. But it is assumed that that jet must be generated from a supermassive black hole at the center of this galaxy. And that's why an experiment was done a few years back to link together radio telescopes across the world in the so-called Event Horizon Telescope using a technique called interferometry, connecting all of these radio telescopes together to actually try and image what's going on in that particular black hole. And they've effectively imaged not the black hole itself, but the accretion disk that is forming around it, like that little cartoon I just showed you. We think that matter is falling into the black hole, trying to fall into the black hole, and in doing so is producing an accretion disk which is getting hot, and that's producing the radiation which is then picked up by this set of telescopes. This is a rather distant galaxy. It's a much larger supermassive black hole than the one at the center of our galaxy, and it is an absolute monster. It is some 6.5 billion solar masses, an absolute huge thing, many thousands of times bigger than the one at the center of our own galaxy. That was chosen simply because it was thought to be big enough to be possible to image it. Now that the technology has been proven, I'm sure they will be imaging other black holes in other galaxies in years to come. But an idea of just how energetic these processes are, if matter falls into a black hole, it can release enormous amounts of energy. And you can get a scale for just how much energy is released by looking at this particular picture of a galaxy called Hercules A. There's Hercules A in the center. It doesn't look very remarkable. It's a rather nondescript elliptical galaxy. Just as a point of scale, there's another spiral galaxy that just happens to be sort of in the neighborhood, as it were. It probably isn't particularly close, but it suits us for a scale. That little spiral galaxy there is probably about the size of the Milky Way. So Hercules A is a big galaxy in the first place, and that gives you a scale from just saying there's the Milky Way to a similar scale. But the supermassive black hole at the center of Hercules A is producing jets, which you can't see in this visible picture. This is a visible picture taken by the Hubble Space Telescope. But these jets are being generated by this tiny object at the center of Hercules A. And even though it's a tiny object, it's generating jets that are visible, not in the visible part of the spectrum, but if you switch to radio waves, then you realize that there are huge jets being generated. So the physical scale of the black hole at the center is tiny, perhaps the size of a solar system. And yet, compare that to the size of the Milky Way galaxy, these jets are tens, if not hundreds of times larger than the Milky Way itself. And these jets the energy of these jets that are flying off into space and smashing into individual atoms that exist in intergalactic space, the energy producing those jets over this enormous scale is coming from the supermassive black hole at the heart of this particular galaxy. Luckily, our own Milky Way black hole is not feeding, is not taking in matter, is not generating energy on this scale, which is just as well, because if it was generating energy like that, it would be a real problem for us at this sort of distance from the center of our galaxy. The idea of matter falling into a supermassive black hole, and if you like, feeding, this is just a colloquialism for if matter is falling into a black hole, then the black hole is feeding because matter is being converted into energy. These systems are called active galactic nuclei if they are in the process of feeding because matter is falling into the black hole. In other words, our own Milky Way galaxy has a black hole, but it does not appear to be feeding at the moment. No matter appears to be falling in to the black hole in the center of our own Milky Way. But the most energetic active galactic nuclei are called quasars, and these emit so much radiation that they can be seen from absolutely enormous distances. And during the lockdown, when I had very little else to do in 2020, I decided, is it worth trying to image one of these quasars? In other words, I knew that they were out there, I knew they could be seen with telescopes. Is it possible to actually capture the light from one of these quasars on the other side of the observable universe, but without using a telescope? So I decided to give that a crack, and spoiler alert, yes, it is possible. I put a camera on a tripod, without using a telescope, took a load of images, added them together, and determined by looking up where I would expect to find this particular quasar. That particular blob there does not look very spectacular. If I blow it up, it still doesn't look spectacular. It is basically 1 pixel in the image taken with this Nikon digital SLR camera. However, the light from this particular quasar, this quasar is some 25 billion light years distant. It is enormously distant. It's on the other side of the observable universe. The light, despite traveling at the speed of light, has taken most of the age of the universe to reach us. In other words, the light was released by this quasar a long time ago, not that long after the Big Bang, and it's been traveling towards Earth ever since for 90% of the age of the universe. So the fact that you can pick up light from one of these objects without using a telescope is testament to the enormous amount of power that must be pouring out of these objects, and they're all being powered from these central engines, these supermassive black holes at the core of galaxies. There's still a lot we don't understand about supermassive black holes. If we look at how big they are compared to the mass of the galaxy in which they reside, then there's the Milky Way, not a particularly big galaxy, not a particularly big black hole, and we compare that to the one I showed with the Event Horizon Telescope imaging the more distant galaxy. That's a much bigger black hole in a much bigger galaxy. There appears to be a rather loose relationship between the size of the black hole and the size of the galaxy in which it's in. So there is a link between them, but we don't understand the nature of exactly what that link is. Chicken and egg, which came first? Did black holes form and then galaxies grow around them? Or did galaxies form in the very early universe and then over time black holes form at the center of galaxies? We don't understand the ordering in which things actually occurred. And that's one of the reasons that the James Webb Space Telescope is looking back in time to the very earliest part of the universe. The further you look, the further back in time you are looking. It's trying to look back to this sort of era to see the very earliest galaxies, to try and understand how did they form in the first place. The Big Bang generated all of the hydrogen, but how did that hydrogen get converted into stars and galaxies? What was the process, and what is the role of supermassive black holes in converting all of that hydrogen into stars and ultimately planets as well? So we still don't understand the answer to that question, and maybe James Webb will give us some clues in the coming years as it does more and more of its work. The third element of the ABC is galaxy collisions. We know galaxies form in the first place by accretion, by gravity simply pulling matter together. But the evolution of galaxies is dominated by the fact that galaxies are cannibals. They eat each other, they interact with each other. Stars in a galaxy are relatively far apart, but galaxies in the sky are relatively close together. Andromeda Galaxy is not that far away from our own galaxy, for instance. So when we look at a picture of a galaxy, pretty though it is, we tend to get this sort of static picture. It's looking rather nice, but a static photograph of a galaxy makes us think, well, that's the way a galaxy is and that's the way it's always been. Yes, they rotate slowly, but apart from that, can we really understand what's going on? We can't sit and watch galaxies to see how they evolve. The timescales are all wrong. If it takes that galaxy 100 million years to rotate once, if we were to sit and watch it for 100 million years, we probably wouldn't learn much other than that's how long it takes to rotate once. We have to resort again to simulations to tell us how would we expect these things to behave. Static images taken, for instance, by the Hubble Space Telescope show us that galaxies are interacting with each other. Some galaxies are in isolation, other galaxies are close enough together in space that they are clearly interacting. One is tugging on the other. The gravity of one is affecting the stars in the other galaxy. So we look at lots of individual static pictures and we can see that quite definitely galaxies are interacting. But to understand exactly what the influence of those interactions are, we really need to run simulations. And again, when we do that, we suddenly realize that galaxies are not large static objects that just look very pretty and sit there forever. When we run a simulation, we realize that galaxies are an absolutely chaotic system. Here we have lots of galaxies in a region of space, a large region of space, a big galaxy at the top, a big galaxy at the bottom, getting closer. These galaxies are getting closer and closer and closer, and those galaxies pass through each other and come out the other side, and then they're pulling on each other, so they are going through each other a second time, and now they are merging into one big galaxy. And as you watch a simulation like this, you realize there's huge things going on in the background as well. I'll just run it a second time, but you can see individual galaxies interacting with each other and distorting each other. That galaxy just got very distorted. This one is about to get very distorted as it goes close to another. That galaxy has just become very distorted. And again, these galaxies are coming close to each other, and galaxies will pass through each other. It's a bit counterintuitive, but generally speaking, stars don't hit each other. Stars are far enough apart that even if two galaxies pass through each other, most of the stars miss each other, but the galaxies still tug on each other through gravity and end up merging together. And when we look at a simulation like this, we say, well, this simulation tells us that surely we're going to end up with lots of big galaxies, the result of merging and colliding with other galaxies, but apparently we end up with lots of smaller galaxies in the neighborhood. Is that anything like what we see? When we look out into the Milky Way is an average-sized galaxy, and it appears to have a few dozen neighbors, a few dozen little satellites, small satellite galaxies. Whereas this simulation would imply that shouldn't we have hundreds of them if this is real, if this is sensible, if this is genuinely taking all the physics into account? Shouldn't our galaxy have hundreds of little satellites, not dozens? Turns out the simulation is right, because we were missing the fact that some of those satellite galaxies are actually quite faint. And now we've looked with better telescopes, we realize, yes, the Milky Way does have actually hundreds of little satellite galaxies, not just a few dozen. So the simulations are telling us, yep, it looks like we can explain the way the universe is. When we look at galaxy clusters, some galaxies are in isolation, but a lot of galaxies are in clusters because they are where these filaments meet, for instance, so there's very dense regions of the universe. And generally speaking, in a lot of galaxy clusters, we find the galaxies tend to be these rugby ball-shaped slightly redder galaxies rather than these smaller disk-like galaxies like these spiral galaxies, a few of which we can see in the background. Why do we tend to find galaxy clusters are mainly red rather than mainly blue? Well, it's because they're crowded. A larger fraction of redder galaxies in these clusters simply because these clusters are crowded, and if they're crowded, they're more likely to interact with their neighbors. And we have determined that when galaxies collide with each other, you tend to lose spiral arms. In other words, this little simulation of what's going to happen when the Milky Way galaxy, top right, and the Andromeda galaxy, bottom left, in a few billion years, they are going to collide with each other. In other words, our closest neighbor is close enough that it will collide with us in a little while. And what happens when two spiral galaxies collide with each other is they tend to completely disrupt the spiral structure of either galaxy. So they pass through each other, and it's not showing up particularly well on this projector, but we're now getting some tidal effects of one galaxy on the other. They've passed through each other, they're now passing through each other a second and third time, and they are settling down into most of the stars being in a sort of rugby ball shape without any of the spiral structure of the original Andromeda galaxy or the original Milky Way galaxy. And that is why most galaxy clusters appear not to be made of spiral galaxies, because they are so crowded, they've already interacted with lots of their neighbors, and they've already destroyed the spiral structure and ended up with these rugby ball shaped galaxies. That simulation gives us an idea of what was going on, but I think more graphic is what would it actually look like from our perspective? We live in a galaxy in which the Milky Way is a band of light across the sky, and the Andromeda galaxy, although it's a huge galaxy, only occupies sort of, that sort of size in the sky. It's about the size of your thumb in the sky. But it is thought that in time, the Andromeda galaxy will start to move towards us. So that will become a more spectacular sight as time goes by. And after about 3.5 billion years from today, the Andromeda galaxy will occupy approximately half of our sky. And at that point, the galaxy will start to pass through the Milky Way. Remember, not quite as apocalyptic as it sounds, because it's unlikely that our sun will be hit by another star, but there will be a riot of new star formation. Whenever one galaxy passes through another, there's so much disruption to both of them, it starts forming new stars. These pink regions here are regions of hydrogen where new stars are being formed. So not only do galaxies grow by colliding with each other and cannibalizing each other, the collision of galaxies is also a catalyst for new star formation. So after about 4 billion years, the sky is going to be lit up with new stars being generated. At that point, it's going to be impossible to say this star came from the Milky Way and that star came from the Andromeda galaxy. All idea of labeling goes out of the window. After 4 billion years, they pass through each other, but they're still gravitationally attracted to each other, which means they will eventually merge into one large galaxy, possibly with two nuclei. Remember, we've got a supermassive black hole at the center of our galaxy. Andromeda has got a supermassive black hole at the center of its galaxy. Eventually, those two black holes are going to merge together into one monster black hole, and that will occur sometime after about 5 billion years into the future. We'll have to decide what we call this new galaxy, because it's no longer the Milky Way and it's no longer the Andromeda galaxy. So we're going to have to do something about that. So we're going to have to call it Milkdromeda or Andrilke or Androway or something. Don't worry, we've got 5 billion years to figure out what the name is, so it's not urgent with respect to that. But we can no longer call it the Milky Way, and perhaps we could still call it our galaxy. It is always possible that the sun will get ripped out of the Milky Way and literally ejected from the galaxy. But even if it does so, the Earth will probably go with it. In other words, it takes so long, it is not so violent a phenomena that the sun will get ripped out of the galaxy and leave the Earth without a sun. If the sun does move, the solar system will probably go with it. But once the black holes do merge together, almost certainly for this new system, Andrilke or Milkdromeda, whatever we're going to call it, almost certainly there will be so much new material for the supermassive black hole to feed on, there will almost certainly be huge amounts of matter falling into the new black hole generated when the two galaxies merge together. And so it's quite possible that the new merger of the Milky Way and the Andromeda galaxy will generate what I called before an active galactic nucleus, or indeed perhaps even a quasar, a very energetic outpouring of energy from the new center of the new galaxy, whatever that we decide to actually call it. It will be bad news for us in the sense that if the Earth is still in existence, going around the Sun at a distance from the center of the Milky Way or the Milky Way Andromeda galaxy, there will be so much energy pouring out of this quasar, it'll be bad news for us. Literally, the amount of radiation produced, even at the distance of tens of thousands of light years, will be a threat to life. We may not be around. The Earth may already have been incinerated by the Sun changing its output, but if we do survive, we'll have to worry about the fact that we could end up living next door to a new quasar. So just to recap, I've had my 45 minutes and a few minutes. So the ABC of galaxy evolution, the three most important factors that determine why galaxies are the way they are, how they came to be the way they are, is that they are accreted under the influence of gravity from hydrogen made in the very early universe, shortly after the Big Bang. We know that there are black holes at the center of every galaxy, but we don't fully understand the role they play in galaxy evolution. And we know that collisions and mergers between galaxies have been absolutely critical to understand how galaxies have changed from the very early universe to the galaxies that we see today, including our own Milky Way galaxy. So next time you see a picture of a galaxy, regardless of whether it's in a magazine, on TV, a picture from the Hubble Space Telescope archive on the web, individual galaxies or interacting galaxies, it doesn't really matter. Whenever you see a beautiful galaxy like this, just remember how they came to be the way they are, the ABC. Thank you for listening.